Okay, so welcome back, everybody. Now it's really the big challenge for me to keep you guys awake when we are late in the afternoon. So if I put you to sleep, you know where you can come back if you have sleeping problems. But let's now try to look a little bit at the classification problem. So one of the thing which we have done till now is basically to try to fit a function to some data. And we have assumed that the data which we have is a data which is given by a continuous function. That's a basic assumption between what we have done till now. But in many, many cases, we are going to have discrete outputs of the type true, false. If you're classifying numbers, handwritten numbers from 0 to 9, you would have 10 numbers. So that would be 10 classes, and you would like to classify them. So that's a discrete type of problem. So just to give you a kind of feeling of the type of fits which we can make, let's now just switch quickly to the whiteboard and take a look at a typical problem, which is it's a very frequent problem in science. And suppose now that we have a data set here, and this data set looks like this. So it's a set of variables where we have x1 and x2 here. And then what you would like to decide upon is whether somebody gets a grade above average according to the number of hours you have studied and the number of hours you have slept. So suppose now we make a survey and you guys register every day how much you sleep and how much you study, and then we look at the final grade you get in this course here, whether that's above average or below average. Actually, here the score is top every time because I always give good grades. I have, this is a weak point, but also when you do project-based work, I mean, people put so much efforts in it that normally the kind of final answers are always excellent. So let's now suppose that the crosses here are observations. So x1 is hours studied, and x2 is hours we sleep. And we make this kind of survey, and the crosses are grades below average, and then the circles are grades above average. And the output is a typical classification problem. So you could say below or above. It means that you have a case here where you could have true, which means above average is equal to the circle. And later you could write this out as number 1. And then you could have false. So this is a binary problem. And false, you could label that in terms of the crosses. And you could give that a number in the machines, because in the machine, when you encode this, you cannot put crosses and circles, right? So the machine works with binary numbers typically. And this is a binary problem. And that means that you would have a problem where you now have either 0 or 1. Or you could label it with -1 or +1. I mean, this is up to you how you label that. Now, if you look at this case here, let me just ask you, could you make a linear regression application to this problem? Because now you want to make a prediction, okay? You want to make a prediction. Somebody gives you the number of hours you studied and the number of hours you slept. And when you have fitted a model to the data here, you want to make a prediction, okay? And could you use linear regression as we have been teaching that till now? Any feeling for that? Suppose you only know about linear regression. How could you use linear regression to make a separation between true and false? Yeah, a straight line. So you could make a fit now where you actually, suppose you fit now, you fit a straight line which goes through the data. That's possible. And then you could say that if the value is above a specific value, then it's +1. If it's below a certain value, it's 0. So you could actually do that. What kind of drawback do you see with that? Some kind of immediate drawback here. There is one particular drawback here.
That you don't know what has more power into, like, our select or the.
Say it again.
Like you don't know which one has more strength, our select or the.
That is correct. Also, you could make many fits here. You could have many lines. There is not only this line. If you just think in a brute force way, you could now actually make many different fits. But let's look, let's try to make this a little bit clearer by looking at another example. Suppose now you also have a true-false case. So we are looking at binary cases. And here you could think the X, which represents the amount of credit card debt you have. And then the function which we have here, P of X, is now the probability of you paying your credit card debt or not. So suppose now the data, so we have this 1, this is you being able to pay your credit card debt, and 0 here is you not being able to pay your credit card debt. True, false, right? So there are only two values. So let's just draw lines here. That's the output. And the data which you would have could look something like this. So if you are below or so a 0 is you defaulting on your debt, and 1 is defaulting on your debt and 0 is not. So when you increase the amount here, you would find more people not being able to pay their credit card debt. You could have some observations here, you could have observations here. So these crosses are the observations. And then you want to make a fit. Suppose now we pick back this straight line, right? So you could make a fit to this data, and that fit could look something like this. This is not something you would brag about as a fit, but suppose this is a fit you make. And you see now that this hits one of the ones or zeros. But if you look at this problem, which you have fitted now, this specific fit you made, that takes values from -infinity to +infinity, right? Whereas we want only values between 0 and 1. So if you look at the line which we have drawn here, suppose this is the fit you make to the data. And since I've been talking about linear regression, you've been so obsessed with that you want to make a first order polynomial fit to the data. And this is what you get. Now, when you make a linear regression, you have a continuous problem, or you have a continuous function you fit it to. So your fit gives you results which span from x -infinity to +infinity, and the value can go from -infinity to +infinity. But what you want is actually something which gives you 0, 1, or allows you to make a screening of the data. So that means that what you would like to have would more be something like this. So you would like a function which you fit, which looks something like this. Then what you would like to say then is that if the value is below 0.5, and you see the curve crosses here, if the value is below 0.5, then you would say that the output is 0. If the value is above 0.5, you would say that the output is 1. So you made a function now, and by looking at this function, you say, okay, value below 0.5, I pay my credit card debt. Value above 0.5, I don't pay my credit card debt. Okay, you see the basic philosophy here? What we want to do, we have a discrete event. So what this means is that when we did linear regression, in the regression case, we had the following. We had our data, and y could then be a variable which took values from minus infinity to plus infinity. And y was now given by a function, f of x, plus some noise here. Okay? This is the basic ansatz here. Now, in the classification case, on the other hand, we are going to make another assumption about the data. So here, if we look at a binary problem, so I need to specify this is a binary case, you are not limited to a binary case. What you have is a discrete set of outputs. So it doesn't need to be just a binary case. You can have as many types of outputs you want, but the case is a discrete set of outputs. And this is the opposite of what we had before, where we had a continuous. We made an assumption about a continuous function describing over y. So in this case, with a binary case, we could now say that y lives is between 0, takes only these two values, 0 and 1. Then what we would do now is that we write y is equal to p of x plus epsilon, where p of x is now a probability. So p of x lives now between 0 and 1. And we assume also that this probability is normalized. So that means that if we now integrate, if this is a continuous function, and we integrate from p of x from, let's say in our case, from 0 to 1. So in this specific case, we could now assume that x is defined between 0 and 1 as well. Or it could be defined from minus infinity to plus infinity. It depends just on the problem which we have. But let's assume that. Then what you have then is a p of x from 0 to 1 of d of x is equal to 1. So we assume that the probability distribution is normalized. So this is a pretty common case which we encounter. So what we are doing now, we are looking after this probability distribution. And there's a very simple one, which many of you may have encountered, which looks like a probability, behaves like a probability. It has all the properties. There's a very simple function which we could now use in order to define the specific event. So let me just call this p of x. And you guys may have met this function before. So it's very popular in neuroscience. And it's used as a way to model the way a neuron would fire a signal based on a specific input. Has any of you met this function before? It has a famous name in the literature. The sigmoid. And that's, if you look back at this specific function here, the one I draw here in red, this has a mathematical shape as an S function, and it's called a sigmoid function. So the sigmoid function, if we look at it, that is given as 1 over 1 plus e of minus x. So this is one of the simple functions which we can make, and we can use that to define a probability for a binary type of case. When you move into more classes, you have something which is called the softmax function. Has any one of you heard of that? So I'm going to come back to that.
1 plus e to the x.
Yeah. So do you guys know where the softmax function comes from? It comes actually from physics. And there was a famous physicist who introduced that back in 1900 in order to describe this black body radiation. Does anyone remember what that distribution is called? It has a famous name. Say it again. It's the Planck distribution, right? And based again on the Boltzmann distribution. So in this softmax distribution, which is a generalization of this sigmoid to more classes, follows or was inspired by the work by Boltzmann and Planck and so on to describe blackbody radiation. So what we are going to do now is actually to look a little bit at the mathematics here and then proceed and see what kind of equations we end up with and how we now can bake in parameters here. Because the way this stands, there are no parameters to fit. Now, since we're doing machine learning, we want to have some parameters we fit in order to find the best possible way to make a prediction of the data which we have. So this function e to the minus x, which we had the sigmoid function, 1 of 1 plus e to the minus x, this was a function we put up now without any fitting parameters. But let's now make a assumption here about the data set. And let me now just bring back the simplest possible way we can do this. So what we could say now is the following. Actually, this should be plus x. I think it's a plus x here, yeah. So what we could assume now is that this probability, this p of x, is now going to be modified to a probability p with a which gives an output y with a given x and a set of parameters beta. And I guess you're familiar with this kind of notation. This bar means that what is the probability of y given x and beta. So x is the input and beta is a parameter, yeah?
Can the function be modified? Because, like, I guess that you can the width
yeah.
can be modified.
Or yeah. Not. So the way we would do that now is actually to write this, and the simplest possible way is to have a linear dependence here. We have a plus of beta 1 times x divided by 1 plus e to beta 0 plus beta 1 times x.
So the beta 0
is a parameter. Okay. Beta 0 and beta 1 are now the parameters which we had, for example, in linear regression. So the betas, these are the parameters. And they're going to play the same role as we had in linear regression, where we had the parameters beta. But you see, there's now a small problem here. And there is an exponential. This exponential is now going to give us a cost function which will not have a linear dependence on the parameters beta. That means that we are not going to find a nice analytical expression for the parameters beta, and we would have to solve that numerically. And that's where optimization methods come in. So suddenly now we are not going to get this nice matrix inversion problem, which we could solve with linear regression. So these are what you're seeing now, these are models which we are making. There's nothing which hinders you to have a more complicated argument to the exponential. There's nothing which hinders you to have more features. So in this case, we have just one feature here, plus one parameter here. But we could have more features, so then you would have a parameter beta 2, beta 3, etc., etc. So like in the cancer data, which I know somebody of you wants to look at, there's a famous data set, which is called the Wisconsin cancer data. You have 30 features. You have something like the perimeter, the radius, the thickness, the area, and so on and so on. So that means that you would have something like 30 parameters you could fit in such a model. And then what you would use this model for is actually to make a prediction and say that this here is now going to be a simple model. So you would say the following. So let's now assume that we take this and we say now that P, and now we modify this P of Y to represent a specific input. So this is going to be replaced by a P of I, and this is going to be P of Y of I. And now, since I've specialized to a binary case, I'm going to assume now that this specific version of the probability is for the case where y is equal to 1. That's my output. And then I have x of I, a specific input, and I have these parameters beta. Then we know that the probability, so let's call this P of I, this quantity, and then I'm going to have a y of I equals to 0 with a given x of I with a given beta. And this is obviously, since we have a binary case, this has to be equal to 1 minus P of I. So keep in mind now that I defined this P of I to be the case where I have y of I equal to 1. No, I have only a binary case, so I have two outputs, 0 and 1. And since the probabilities are normalized to 1, you see now that if I add the two probabilities, that sums to 1, right? So if I take now the probability of P of I, y equal to 1, plus P, and I'm skipping x of I and y of I equal to 0, this simply sums up to 1, because that is the same as P of I plus 1 minus P of I. And you can see that if you sum up the two probabilities, this is actually going to happen. Okay? So keep in mind that we are just making models now, okay? And we are going to use this function as just one function to describe a probability for a specific output. Now, what we haven't done is to find the parameters beta 0 and beta 1, which describe our data. So you see the basic philosophy? So instead of looking at the continuous function f of x, we are now going to parameterize something which is going to behave as a probability. And we are going to say that if this p, when we calculate it with the parameters, is less than 0.5, you output 0. If this p is larger than 0.5, it outputs 1. So when you calculate this function p, it's not going to give you 0 and 1, but it's going to give you a value. And then you have to put an if statement saying that if the value is less than that, 0. Larger, 1. So the philosophy is pretty simple, but now we need to make a cost function based on this. So the way we can define now the whole situation is to assume the following. So we are going to assume that we can make a general probability. So we have a domain of events, which now contains x0, y0. It contains x1, y1, etc., all the way up to xn minus 1 or yn minus 1, like this. And we want a probability distribution for this set of events, and I'm simply going to write it like this. What is the probability of finding this domain of events D with a given value beta? So this is what we want to calculate. We are now going to make an assumption about the data. So the assumption is that these events, P of I, or the Y of I, these Y of I's are independent variables. So I here, independent, and identically distributed. That's a basic assumption we are going to make about the data set which we have. So you see now when we build up these analysis tools, we make some basic assumptions about the data sets. This may not be true. We may not know that the probability for these Y's is governed by something which we could characterize as independent variables and identically distributed. But what we're going to say then is that these probabilities, the P of D with a beta now, they are going to be given by the product of the individual probabilities. And then we have this P of I. And now we have to be a little bit careful here, because we actually defined the probability in terms of two possible outputs. So this is going to be to the power of y of I, and you may have seen such a formula before, and 1 minus p of I, and this is obviously to the power of 1 minus y of I. So if the output is 1, then, so if we have 1 here, then you see that this term here is obviously given by 1 minus 1 to the power of 0, so that's 1. And then this term here is now going to be the only one which dominates. So if y of I is equal to 0, then this term is going to be 1, and then I'm left with only this term, right? So this is now my probability of a binary output. So I take the individual events as a product of the probability for 0, multiply with the probability for 1, but with the given powers. So you see now with the power y here, then I guarantee that's only the output y equal to 1, which gives something. And if I have a y of I equal to 0, then it's the second term which dominates. So this is now my model for the probability, okay? Now, what would you prefer now? When you want to find the parameters beta, would you like to have maximum probability or minimum probability? So if you now, when we now want to define, to find beta, which best describes the data, what should we aim at? What should we aim at in the optimization? In the optimization. So because we want the optimal parameters beta. And then I'm going to leave you optimization. Let me just correct that one. In the optimization of P, because this is now going to define our cost function. So let me give you two answers. Max, the beta which maximizes the probability, or minimizes the probability. So this is an intuitive answer. This is a question about your intuition. If you want something, do you want to maximize the probability or minimize the probability? Yeah?
I don't get what is the P, the given beta.
P, this is the, what is the event? What is the probability of finding these outputs given the inputs you have with a given value of beta?
I still don't get it. I'm sorry. What is the probability of finding one value?
So if you look at this quantity you have here, I should actually have written this one. Let me just rewrite it. So you would normally see this one written like this. So I have a P of I, X of I, with a given beta. So I fix beta, and then I'm asking myself, so what does this probability like? So you fix beta, and then you obtain a probability for Y within a given X. So Y and X are your data. What is the beta which reproduces best the probability of having Y and X?
Okay.
This is what you're asking. So this bar here means what is the probability of a given output with a given parameter beta. So that's what it means from a probability point of view. It's just a notation, right? So you're just asking the question, you're producing a probability with a given parameter beta. And now you're asking the question, what is the optimal value of beta for this probability? And when you're asking the question, what is the optimal value of beta, you would ask, do we want to look at the maximum probability or the minimum probability? So if you're constructing a probability for some type of events, would you prefer to have the minimum probability or the maximum probability? The maximum, right? So when you're asking yourself, what is the probability of becoming a lotto millionaire? you're not looking after the minimum probability, right? You're looking after the maximum probability, right? So sadly, there is no transformation which transforms your probability to higher probability to become a lotto millionaire. The probability to become a lotto millionaire is fixed. So what we are looking after now is to find a parameter beta, the optimal beta, which is now the maximization of this P of D of beta with the values of beta which we have this range of parameters beta which depends on, which have a length P. This is what we want to do. Now, if you look at the function we have defined, if you look at this function up here, which is now the product, this product follows from the fact that we have assumed that the total probability is a product of the single probabilities. Because we have assumed that they are independent and identically distributed. So every single event Y is given by the same probability. Now, if you look at this function here, now since you want to optimize, what we want to do then, this problem here, that leads to us calculating the derivative of this D of beta with respect to beta, and we want that to be 0. Mathematically, that's what we want to do. We want to calculate the gradient. So if you go back and look at this function, is there an equivalent function which allows you to calculate this derivative in an easier way? So you have a product. There is a function which has an, yeah. So instead of defining the equivalent problem is to optimize the log of this function. And the log is a simple additive function. And then it's much easier to calculate the derivatives. So the equivalent problem is to actually calculate. So we would now calculate the derivative of the log of P, of D of beta, with respect to beta. Now we know that the log is a monotonously increasing function. So that means that we have a derivative which corresponds to a concave problem. Now what we could do, if we prefer minimization, what could we do then? So now we have the positive log, and that gives us a concave problem, a maximization problem. If we prefer the minimization problem, which we normally do in physics, what would you do then? A minus sign. So instead of maximization, we could now minimize. So the equivalent problem now, if we want to do a minimization, is to do an arg min of beta in this domain of this range of values of minus the log of P of D with a given beta here. So if we do that, then the thing we need to do is actually to calculate all these nice derivatives. So let me, and this is going to define our cost function. So this quantity here is going to be the cost function C of beta. And if you now calculate the log of that one, you will find that this C of beta is actually equal to a sum minus, and this runs over all the data set which we have, y of I from 0 to n minus 1. And I'm just going to give you the answer here without the intermediate calculations. So you can show that this one is going to be equal to y of I, and then it's going to be multiplied with the parameter, let me see now, what did I do wrong here? y of I. Yeah, it's y of I multiplied with e of beta 0 plus beta 1 times x of I, and it contains plus, naturally minus. It's a minus here, minus, and then I have log of 1 plus e of beta 0 plus beta 1 multiplied with x of I. And then I can calculate the derivatives with respect to beta 0 and beta 1. These are the parameters. So if I do dc d beta 0 and put that one to 0, that is going to give us minus I equal to 0 of n minus 1. And then I have y of I minus. And what you will see then is this is going to be given by p of x of I, where now this p of x of I is a function we defined as e to beta 0 plus beta 1 times x of I divided by 1 plus e of beta 0 plus beta 1 multiplied with x of I. So if you just take the derivative of that function, which we have with respect to beta 0, you will get this value. If I take the derivative with respect to beta 1, then this is also something we want to drive to 0. And this is going to be given by minus a sum from I equals 0 of n minus 1. So I'm not, in the lecture notes, actually, you will find the intermediate steps here. But here I just thought of just setting up the final results. So these are actually two gradients. The general expression, when you have more than just two parameters beta, you can actually rewrite this in terms of a matrix multiplied with a vector. So you have a dc d beta, which is equal to 0. That's something you can rewrite as minus x transpose of y minus the probability p. Now I'm writing these as vectors. So keep in mind now that x is your design matrix, y is the set of outputs. So that would be a vector y0, y transpose is y0, y1, y2 up to y of n minus 1. This vector p, so this has a length n. This vector p here is something which has vector p transpose is equal to p0, p1 up to pn of minus 1. And that has also length r times n. And then we remember that this design matrix, the design matrix itself, is something we defined to have dimension n multiplied with the number of features. So you see now that this dc d beta is a vector of length p. And you can see that when you perform the multiplications here, you have x transpose. So that is a matrix of dimension p times n. And you multiply that with two vectors of length n and n. So that gives you a derivative here which has length p. So if you have two such parameters, beta 0 and beta 1, you see now that this obviously has length 2. And this will be given by these two terms which you see here. This is a gradient of the cost function. Now what you see here now is that this gradient is actually something which now does not depend in a linear way on the unknown parameters beta. So if you look back here, we see that the dependence on beta is hidden in this function p. So compared to the previous case when we did linear regression, so let me quickly remind you of that. So in linear regression or ordinary least squares, what we had then is that the derivative of the cost function was then given by the function which went like minus, so we had 2 divided by n, we had x transpose, and then we had y minus x times beta. And that meant that the parameter beta, the optimal ones, were given by x transpose times x minus 1 times x transpose times y. So here we had a linear dependence on beta in the model. Here we don't have that. Here we have that dc of d beta, and now I'm just going to rewrite the equations. It's going to be given by x transpose multiplied with p minus y. And this depends, p now has a nonlinear dependence on beta. So we don't have a nice analytical solution of the unknown parameter beta. So this has to be solved numerically. Now, there's one thing I wanted to just list for you before we take a break. We can calculate the second derivative in terms of the parameters beta, and that's going to be given by this quantity. And compared with what we had earlier, this will now depend on a matrix W, which has only diagonal elements. And these diagonal elements are given by px of I multiplied with 1 minus px of I. So only diagonal elements. So this is W is a diagonal matrix. And you can show that when you do the calculations here. And this defines a matrix which is called the Hessian. So this is the second derivative of this cost function. This matrix is also going to be positive definite. So it means that we are dealing with a concave problem. There's going to be a global minimum. However, in our case, when we now want to find the value for beta, we need to resort to numerical calculations. So the function we want to put to 0 or find the roots of is now the gradient of the cost function. So if you now spool back, before we take a break, to the way you found the root of a function, how would you find the roots of such a function where the function is 0? What is the first method which comes to your mind besides the simple midpoint method or the second method? There's a famous method of a famous physicist, Newton method. It's actually called Newton-Raphson because Raphson was Newton's assistant. So the Newton-Raphson method is where we're going to start after the break. And I'm going to set up how you would typically calculate these equations. And then we are then going to set up the optimization problem. And then you will see all the nastiness coming up and how we actually calculate this type of gradients and how we optimize the equations to find the roots of the gradient. So essentially now we have a different problem from linear regression. So we have a non-linear dependence on beta. And this is our first encounter of, the more general type of problem, where the equation now doesn't have a nice analytical solution for the gradients. And this is essentially what we have to live with when we do machine learning. So you guys have been extremely patient, and I think everybody needs a coffee. So if we could take a break now, and then after the break, I'm going to scratch the surface of the first optimization part. And then next Monday, we are going to dive into the way we deal with the optimization. So I'm just going to use at most half an hour after the break, and so that we are done a little bit before 6. So I don't spoil the evening for everybody here. So So what we did before the break.
Sorry, I need to take this out.
Yeah. So what we did before the break was actually to prepare the basic ingredients for the optimization part. So if you look at the equations which we have a general equation for the gradients, and we have a general equation for the second derivative. Now, if you now want to find the roots of the gradient, so the gradient is now given by the equation which you see here. This is actually what we want to find the roots of. One of the standard methods is to use is actually Newton's method. So let me just give you a quick reminder of Newton's method. So Newton's method is nothing but a Taylor expansion around a point, and you keep the term to second order, period. That's Newton's Raphson's method. So if you think of that method, so let me quickly remind. So what we want now are the roots of dc d beta equal to 0. So if you now look back at Newton's method, or Newton-Raphson method, then what we want now, and I'm just going to write a function, we want a function of f of s equal to 0, where s now is the optimal parameter. And the way you would typically do that is to make a Taylor expansion around s or x plus some parameter. So the way you would do that is to Taylor expand around a f of s plus some delta x here. So what I'm going to do now is simply to bring up the slides, and I will show you where in the slides you will find this type of equations. And next week, so I'm going to be short now, I don't want to steal too much time. So next week we're actually going to look at the optimization part in more detail. So now I just wanted to set up the equations so that you see what the problem is. And if we now go back to the Jupyter notebook, so let me just bring up that, and then you can see where you will have all the mathematical details. So if you scroll down, so we went through this logistic regression case. So let us just scroll down a little bit and look at the, let me just go down. I'm going to jump back a little bit to many of these problems. So if you now think of you making a Taylor expansion around a point s minus x, this is a general formula, right? Now, this means that, or normally what you do now is that you truncate the equations and you leave out terms beyond this linear one, which are not important. And you end up with an equation for this parameter s, which is given by x minus the derivative, f of x minus the derivative of x, of f of x. So this is just you truncating the Taylor expansion around the point. And this is something you solve in an iterative fashion. You start with a guess, and then you keep solving this equation here till you have obtained a difference between x in iteration n plus 1 minus x at iteration n, which is smaller than a given number. That's Newton's method in essence. So it's not very fancy. It's a Taylor expansion, which is the basis. Now, in our case, the thing is that this function f of x is the gradient. So we want the gradient to be 0. And that means that we have to divide it when we are doing more than one variable. So if we move beyond the one-dimensional case, we end up with taking the inverse of that matrix we call the Hessian, the second derivative. So you see, all the root of all evil here lies in the term you have here, which is the second derivative of the cost function, which is a matrix we have to invert. So if you go back to the slides here, let me just bring up the regression case. This is the gradient, which we want to drive to 0. This is the second derivative. So if I now perform an iteration instead of x, I have my iteration in terms of beta. This is the equation I have to solve. So that means that I have my old value. I calculate this matrix for the old value, which is my Hessian matrix, the second derivative, and I calculate the gradient at the value beta old. And then I keep iterating till this difference is smaller than a given number. So in this typical case, what you would do, since it's beta is a vector, you would just calculate the norm of the vector and the norm of the differences between the previous one and the new one. And if that is smaller than a certain number, you stop. And you see now that if you just have few parameters, suppose you have a 2 by 2 matrix, you can do this. Because for the inverse of a 2 by 2 matrix, you have even an analytical expression for that. So this is something you can do with small matrices. If you run into neural networks, this matrix, which you see here to invert, can have a dimensionality of 1,000,000 times 1,000,000. And if you then have 1,000,000 parameters, and you do 1,000 iterations, you can then easily calculate the number of times you're going to make an inversion of a matrix here. So this means that it's not feasible. Okay? It's basically you will not calculate the inverse of that matrix, except for some simpler cases. So let me now ask you one thing, and we are going to not go much more in detail. I'm just going to show you some simple cases. So if you look at this guy here, this matrix to be inverted, times the gradient, what is the simplest way to avoid the calculation of the gradient? Oh, no, not of the gradient, of this matrix here. What could you do as a quick fix?
Set it to 1.
You could set it to 1, or you could, say it again?
Not invert.
Not invert, yeah, we don't want to invert, right? So the whole optimization, when you would not like to invert, so what could you replace this quantity with? So if you think back to the Taylor expansion, you don't want the high order terms to blow up, right? So you would typically like to have them less than 1, because else terms may blow up. So what could you do now? It's a very quick fix.
To renormalize your betas by multiplying.
That comes a little bit later. So you could then have an adaptive value here, right? Some adaptation, which means that you are multiplying with a constant. So the way this is normally done in all machine learning algorithms is to replace the second derivative with a constant. And that becomes a parameter, which is called the learning rate. And I can see your disappointment here. Because, hey, we are going to tweak a new parameter. We talked about this hyperparameter lambda, and now comes a new parameter. Actually, this learning rate is what leads to all these ways of finding the learning rate in an adaptive manner. So this algorithm I mentioned, which is called ADAM, adaptive momentum, or there is ADAP-GRAD, adaptive gradient, means that you find a way to tune these parameters here. So what we're going to do now, instead of, so let me just bring back the whiteboard, because then we have the basic root of all evils, which we are going to meet in machine learning here. So if we look at these parameters beta, so what we have now is a beta optimal for the new value, the beta new, which is actually given by the beta old. And what we had is the inverse of this Hessian matrix, which depends on beta old. So we would have to evaluate this matrix at the previous values. So that itself is expensive from a computational point of view. So we need to take the inverse of that one, and we multiply this, and I just write this as G, as a gradient, calculated at beta old. So the gradient is a vector. And that's also something, if you have millions of data points, this becomes time consuming. And there are efficient ways, which is called stochastic gradient descent, where you don't evaluate the full gradient for all the data points. We are coming back to that next time. So what is normally done then is actually to replace this one with a parameter gamma. So this parameter gamma can be made into a parameter which changes from iteration to iteration. So there is a scaling here. And this leads to the whole field of gradient optimization and learning rate optimization. So this parameter is called the learning rate. And this becomes a parameter in the theory. And it's actually cheaper to run the calculations with different learning rate parameters than to calculate the inverse of the Hessian matrix. So if you now think of, like the cases we have seen till now are small cases. We had few parameters. But when we come to neural networks, you're going to have millions of parameters. And that means that when you have millions of parameters, the calculations of both the gradient and this matrix to invert, they are going to steal all the CPU time. And then it's actually cheaper to replace the calculation of this matrix to invert with just a set an array of parameters gamma. And then next week, so I'm going to stop pretty soon now because I didn't want to steal too much of your time now. But next week, when we meet for the regular lecture on Monday, we are going to pick up the discussions of this convex optimization problem and the determination of the learning rates. So this leads to tons of methods to calculate this quantity. We have things like ADAGRAD, adaptive gradient. We have something which is called root mean square propagation. We have a stochastic gradient descent. Stochastic gradient descent. So we need to discuss these methods a little bit. Descent. We have ADAM, which is adaptive gradient with methods, and so on. So all these methods aim at finding a way to adapt this learning rate according to the number of iterations which we are making. So an optimization problem doesn't sound like the most fancy problem to deal with, but this is really the bottleneck of basically all machine learning methods. So when I said that if you can make a contribution to the improvements of these methods, this is where you will get many more friends, and these friends will cite you. I don't know if these kind of friends are the friends you want to have, but if you care about the number of citations, then it can be okay. And as I said, this ADAM algorithm, if we can just end the day here. And actually, I wanted to ask you to take a look at the slides which we have here, and from the part where we start solving Newton-Raphson methods till the end, this is where I want to start next week. So I used logistic regression as a way to motivate the introduction of gradient methods, simply because logistic regression is the first case we meet of what we call low-level machine learning methods, where we don't have a nice analytical expressions for the optimal parameters. And we need to solve the equations numerically because we have a nonlinear dependence of the parameters beta. And that allows us to motivate the introduction of these gradient methods. And machine learning has, as we said in the very beginning, at its heart, there is an optimization problem. And you can look at here, just to tease you a little bit. Let's just bring that up. So let me just, and that's where we stop today. And let me just bring that. So here, and we just write citations for Adam. Not Adam Smith, but Adam method. And this is something which keeps, and you can see the number here, right? 124,211 citations. That says everything about the importance of these gradient methods. As I said, a famous paper in physics has 100 citations roughly. So we are talking about 3 orders of magnitude. So next week, we are going to discuss these gradient optimization methods, because I wanted to sneak that in as a task in the project so that you actually test it yourself. And then when we're done with that, we are going to go into deep learning and how we set up a neural network and what that actually means. And that will keep us busy till roughly the winter break. That's the kind of idea and the plan with the lectures here. Okay, so I'm going to stop here so I don't ruin the rest of your evening here. So I'm going to stop